we get to think about the most fundamental questions in our universe. We are literally thinking about the Big Bang, black holes, our cosmology, how it evolved. This is something that not many people get to do.
It's in a way about appreciating nature in a different way, understanding the mathematics that is hidden from us. And if we can understand that, we can have a better understanding. It satisfies our curiosity.
One of the kind of very cool things about being a theoretical physicist is that you're following in the footsteps of some people who everybody has heard of, like Albert Einstein or Stephen Hawking, or more recently Oppenheimer. Our project is essentially just a follow-up on the work that Oppenheimer did back in the day.
Hi, my name is Mark, and I'm a professor in the Department of Physics and Astronomy here at UBC. So the focus of my research is quantum gravity. That is sort of the intersection between quantum mechanics, which is what we usually use to understand microscopic physics, atomic scale physics, molecular scale physics. And then the other aspect is gravity, which is usually understood through Einstein's theory of general relativity. So that's the curving and warping of space-time when it interacts with energy and matter. We're trying to combine two of these great theories developed in the 20th century into kind of one unified mathematical structure. Physicists would like to combine those two things because there are questions where we need both of them to understand. So questions like understanding the origin of the universe, the Big Bang, understanding the physics of black holes and specifically what's inside a black hole, understanding exotic things like dark energy, wormholes. All of these questions require, we think, a more complete theory than we have so far. So let me tell you a little bit about the specific research that I've been focusing on actually for the last 10 or 15 years. And it's completely wild. So this is an approach to quantum gravity called holography. The idea is that our 3D space that we live in and observe is not quite as real as we think. To understand what that means, the analogy I like to give is it's a bit like a computer chip that's encoding the physics of a 3D video game. Every state or configuration of the two-dimensional system somehow encodes the physics of a three-dimensional universe. And so it's a little bit like that, where we think maybe our 3D gravitational universe that we observe is actually more fundamentally described by a 2D simpler universe that obeys the rules of quantum mechanics and electromagnetism and so forth. We are trying to figure out the code, how the 3D physics of gravity is encoded in that 2D universe. So my work is very theoretical, and so that means that I'm not interacting with experiments on a day-to-day basis. I'm not doing experiments myself. There are a lot of experiments out there that have already been done. There are a lot of observations that have already been done, and these previous observations and experiments have left us with various kinds of puzzles. So one good example is the observation that our universe is expanding, and more specifically, the observation that this expansion is accelerating at the present time. And so this is something that is well accepted. It's verified by observations, but we have no idea why that's happening. how could we extend our current mathematical models of nature in order to have a consistent mathematical explanation of something that would act like this dark energy, something that would cause the universe to accelerate. So the toolkit for my research is mostly mathematics and a little bit of computation, a little bit of coding, using computers as a tool to do some of the calculations that I want to do. And then together with those things, of course, in the background, there are all the concepts in physics that I need to make use of and understand. Often we have some big questions like, what really happened at the Big Bang? And we'd like to make progress on those, coming up with a simpler problem that would get us partway towards the answer to the big question that we're interested in.
So working in theoretical physics, you want to be able to build models which consist of a set of simplifying assumptions. So you're trying to ask a question and you want to simplify that question, and it may not necessarily correspond to the real world example that you're trying to study, but you simplify it so that you can write the math and you can just use the laws of physics and equations to predict for you what will happen later in time or in different scenarios. So we usually build these toy models in physics and study what they imply.
When Stephen Hawking did his calculations, which showed that things can leave a black hole, he made certain assumptions. Just because it's very difficult to do these things, you have to make assumptions as you go. And so I've been trying to relax some of the assumptions in order to try to understand this a little bit more realistically.
In the first half of my day, I normally think about what can be my next new project, and so I have some vague ideas which are initially in your research you just have some ideas or what kind of thing you want to do or what kind of question you want to answer. However, it's not a sharp enough question that you can just go out and solve. So there is some amount of time involved in which you're surveying papers, you're looking at what people have done in the past, or even just learning new techniques and or sort of a language in which you can formulate your question so that you have something precise that you can answer.
In most cases, what you'll find is that there might not even be an answer, or that the question you're asking doesn't even make sense to begin with. So doing research is a very non-linear process. I've found in my experience as well, I've definitely asked the wrong questions more than I can count. And sometimes you will just fail, and that's okay. That's part of the process, honestly.
So when I took my first sabbatical in 2009, I started thinking about some connections between a field called quantum information theory, which is related to quantum computing, and the field of quantum gravity. And I wrote all these observations down. I probably worked for 6 months, and then I wrote a paper, and I was very proud of this work. It was one of my favorite papers that I'd ever written up to that point. And so I sent it off to the journal, and it just got rejected, the first journal I sent it to. And the referee report made me feel like I was a crackpot physicist sending some wild idea. Then I just went on and sent it to the next paper, next journal, and they rejected it as well. And ultimately, after 3 or 4 years, that direction became one of the hot topics in my area. And so then that paper now is one of my most cited papers.
there's this idea that people who study sort of fundamental questions, they must be like smart or like super good in math or everything. But I think for me, it's been much more about just keep asking questions and being curious.